All right, welcome everyone to our Quantum Matter seminar series. My name is Adrian Fagin, and I'm hosting together with my postdoc, Krysia Savatsky. We like to keep the introduction brief, so it is my pleasure today to I'm sorry, I'm having some technical issues here. All right, it's my pleasure to introduce Christian Batista from the University of Tennessee in Knoxville and Oak Ridge National Lab. And today he's going to be talking about some recent work he's done on systems with Spinorbit coupling. Please, Christian, go ahead.
Okay, thank you, Adrian, and thank you, Krysia, for organizing these seminars and giving me the opportunity to share this seminar with all of you, also to the ones that connected today. And let me start by also acknowledging my collaborators. So Shanshun Chang is a postdoc in my group at the University of Tennessee. Hao Shang, he's a student. Hiroaki Ishizuka, he's an assistant professor of the University of Tokyo, and Gabor Halash, that is a staff member at Oak Ridge National Laboratory already, for more than a year. And today, the outline of what I would like to tell you today is quite simple. I will start, with a very brief introduction to the anomalous Hall effect that was discovered during the 19th century. And then I will quickly move to what is, is the so-called intrinsic anomalous Hall effect that was essentially discovered by Karplus and Lattinger. And that will give us the motivation to introduce, anomalous Hall effect, not just in ferromagnets, but also in antiferromagnets, and see how, what is the emergent U1 gauge field, right, that can be produced by an antiferromagnet, and in the end, lead to anomalous Hall effect. So I will start by explaining, what is the origin of this emergent U1 gauge field when you have an SU2 invariant theory, in other words, in absence of spin-orbit coupling. So we will see that this emergent U1 gauge field is related to something called scalar spin chirality that measures the degree of non-coplanarity of our magnetic texture. And then the contribution of this work will be to introduce the spin-orbit coupling in the theory and see how that notion of scalar spin chirality generalizes in the presence of spin-orbit coupling, right? What we will see essentially is that this emergent U1 gauge field that leads to anomalous Hall effect has actually a more general expression that includes the scalar spin chirality as a limit, right? So you will find a covariant expression of this emergent U1 gauge field. And this result, will help us to understand something that, was reported, over in different materials over the last, I would say, 6 to 7 years, which is the fact that, both coplanar and collinear antiferromagnetic orderings can also produce anomalous Hall effect. And, I will discuss, if time allows, I will discuss the case of manganese 3-tin, that is one of the most well-known materials, since the paper of Satoru Nakasushi, that exhibits, it's an antiferromagnet, it is coplanar, it exhibits a very large anomalous Hall effect, right? And actually, I have to say that everything that I will tell you today was motivated by a question from an experimentalist, from Satoru Nakasushi, who, precisely asked me this question, how is that, coplanar antiferromagnets can also produce a large anomalous Hall effect. So the story starts a long time ago, right? As you probably all know, Edwin Hall, discovered the Hall effect in 1879. In his words, he said when a current carrying conductor is placed in a magnetic field, the Lorentz force presses its electrons against one side of the conductor, right? And in other words, what this means is that the off-diagonal component of the resistivity tensor is now proportional to the magnetic field, and the proportionality constant is the so-called Hall coefficient that depends on the concentration of carriers, right? So, but what is perhaps as remarkable as the discovery of the Hall effect is the fact that 2 years later, Hall reported that when you measure this effect in metals that are also ferromagnetic, there is an extra contribution. I mean, actually, the Hall effect can be 10 times bigger than in non-magnetic metals, and this extra contribution that he reported to be proportional to the magnetization is the so-called anomalous Hall effect. And unlike R0, unlike the Hall coefficient, Rs, right, depends on many details of the material under consideration. And actually, it has extrinsic and intrinsic contributions. And it took a long time. Actually, it took until 1954 to understand, the fact that there is an intrinsic contribution to this anomalous Hall effect. It was a work by Karplus and Lattinger, right? Who essentially noticed that once you include the spin-orbit coupling, right, the magnetization, the spin magnetization of the electrons via the spin-orbit coupling, will act as an effective field that is orbitally coupled, to the conduction electrons, and therefore, will produce an additional contribution to the Hall effect. But what is interesting is the way they arrived to that conclusion. When they did the actual calculation, they found that when you write the equation, the semi-classical equation of motion for electrons moving in the conduction band, there is an anomalous contribution to the velocity. So the usual expression is this group velocity, but they found out that there is an anomalous contribution, anomalous velocity they call it, that is proportional to the cross product between the external force or the external electric field and an effective field. That is what we know nowadays as the very curvature in momentum space. So this expression that appears here, where here this effective field is the curl of an effective vector potential, that is the so-called Perry connection in momentum space. So essentially, the origin of this anomalous velocity has to do with interband matrix elements of the current operator. And when you project your degrees of freedom on only one band, what happens is, as it is known, in general for operators, I mean, so if you have operators that like the components of the position operator that commute in the original Hilbert space, once you project, right, in a subspace, these operators do not necessarily commute. So for instance, the position operator, typically, as we know, is the derivative as a function of a momentum operator, but when you are projecting it into the conduction band, there is another contribution that is precisely this so-called Berry connection or vector potential that makes this operator covariant. In other words, this operator must preserve its form under a local gauge transformation in which we multiply each of these block states by a phase that is momentum dependent. So it's because of this additional contribution that when we compute the commutator of the position operator with the Hamiltonian to get the velocity, we will get this extra contribution that in the end will lead to the anomalous Hall effect. Now, something that was discovered also later on is that the anomalous Hall contribution is not really always proportional to the magnetization. So actually, you can find several ferromagnets where the rho xy is actually has a non-monotonic dependence as a function of m, right? Meaning that in principle you could ask, if that is the case, if the magnetization is not necessarily the only parameter, if antiferromagnets can exhibit also anomalous Hall effect, right? So based on that observation, one could ask if antiferromagnets can also produce this spontaneous anomalous Hall effect. And of course, the answer is yes. And one way of understanding this in a very simple way is to use this very simple model, the so-called SD model. The last time I gave this talk, I said that this model was introduced by Zener in 1951, but my friend Sasha Chernyshev made me notice actually that this model was introduced by two Russians in 1936, Shubin and Konsovsky. And apparently Shubin was a genius that, unfortunately died during the purges of Stalin. So anyway, so this is a very simple model that was introduced to describe the physics of incomplete D shells, so like transition metals where the D shell is not complete. So let me use, for instance, the manganites as an example, where you have, local moments. In the case of the manganites, the local moments will correspond to electrons that are localized in the T to G orbitals, right? And we will use a classical approximation to treat those local moments. So we'll have this classical vector field associated with the local moments, and those moments are coupled via Hund's coupling, right? Via this exchange that is ferromagnetic with the spin of the conduction electrons, right? The conduction electrons, that in the case of the manganites will be electrons, let's say, that are moving, in the EG band. They basically, the kinetic energy of these conduction electrons is described by a simple tie-bonding model, right? That, where the spin of the electron is, the spin orientation of each electron is preserved. So, this term, as well as this one, both are SU2 invariant. So there is no spin orbit coupling in this version of the model. So a few years later, a few years after Zener, Anderson and Hasegawa considered the double exchange limit of this model. So you can assume that, the Hund's coupling is, let's say, much bigger than T, and, try to understand what happens in that limit. And in that limit, it is clear that, the spin of the conduction electron is now forced to remain parallel to the local moment, right? So the orange arrows here are the local moments, right? And what this figure is indicating is that at low energies, because we are assuming that the Hund's coupling is strong, the spin of the conduction electron is forced to remain parallel to the local moments. And as a consequence, if we use the degenerate perturbation theory, when the electron hops, right, from one side to the other one, now we have to project the final state, right, the final spinor that was along the N1 direction. Now we have to project it along the N2 direction. In other words, the effective hopping amplitude is the Baire hopping, the original hopping, times this inner product between the two spinors, N1 and N2, right? And the important observation is that this renormalized hopping not only has a different magnitude, but also now it can have a phase, right? This inner product, will introduce a phase. And that phase has a geometric interpretation. So that phase is simply the solid angle spanned by the two vectors, N1 and N2, and a third vector that, corresponds to the direction of our quantization axis, right? So the phase associated with this effective hopping now that we have in the double exchange limit is simply given by this solid angle. And of course, this solid angle will depend on our choice of the quantization axis. But if instead of computing just this phase, now we compute the sum of this phase plus this one, so in other words, the circulation of the phase, or the very phase that the electron picks up when it moves in a closed loop, that will be the sum of the three solid angles, and the sum of the three solid angles is simply the solid angle spanned by these three vectors, N1, N2, and N3. It does not depend on the orientation of this one. Right? So in other words, unlike the very connection, the very phase, right, is the solid angle spanned by these three vectors, is independent of the choice of our quantization axis. And of course, you have to divide by 2 because we are dealing with spin and half. So essentially what we are saying now is that, when the electron moves around this loop under the constraint of keeping the spin parallel to the local moments in N1, N2, and N3, it picks up a very phase given by this expression that cannot be distinguished from the Boma-Haranov phase that the same electron will pick up if there were a flux, right, in this plaquette. Instead of these three moments, we had a flux. And this allows us to connect, right, to establish a connection or a equivalence between, this, non-coplanar configuration of spins and an effective flux, right? The effective flux in units of the flux quantum, right, multiplied by 2 pi, is simply the solid angle divided by 2, right? Now, you know that the solid angle, when the spins are quasi-parallel to each other, is approximated by the triple product, right? The so-called scalar spin chirality. So in other words, what we are saying is that the effective magnetic field produced by a non-coplanar magnetic structure is proportional to the so-called Skyrmion density or scalar spin chirality, right, of the underlying magnetic moments. Moreover, if we change one of these space derivatives by a time derivative, in other words, if we assume now that these local moments are changing in time, right, not only we have an effective magnetic field that is orbitally coupled to the conduction electrons, now we also have an effective electric field, right, that is given by this expression. So in a few words, this underlying spin texture is producing an effective U1 gauge field, right, with electric and magnetic fields that couple to the conduction electrons, right? And looking at this expression, right, we can see that what we need to have an effective magnetic field is a spin texture with a finite Skyrmion density. So the first example that I will consider is, of course, a Skyrmion crystal. I mean, it is pretty clear that if we have a Skyrmion crystal, an antiferromagnetic ordering that corresponds to a Skyrmion crystal, then according to this formula that I wrote here, right, every time the solid angle spanned by a Skyrmion is 4 pi, right? So 4 pi divided by 2 is 2 pi. That means that one Skyrmion corresponds to one flux quantum, right? So in other words, if we have a Skyrmion crystal like this one, right, the number of flux quanta is equal to the number of Skyrmions, right? And definitely this is producing an effective magnetic field that couples to the conduction electron, so this should produce an anomalous Hall effect, and indeed that is the case. Let me say also that these Skyrmion crystals were predicted by Bogdanov in the 80s, and they were found in manganese silicide by a German group in 2009. One of the ways in which we can check if there could be a Skyrmion crystal, let's say, in a given material is we know that it should produce an anomalous Hall effect. Moreover, I think there is a recent paper by Tokura in a gadolinium-based, by Tokura's group, in a gadolinium-based material, where they report a giant anomalous Hall effect, produced by a Skyrmion crystal. Now, someone could complain and say that, actually, in all these materials that exhibit Skyrmion crystals, there is still a net magnetization, right? Because these Skyrmion crystals are induced by magnetic field, right? So besides the antiferromagnetic component, there is also a ferromagnetic component induced by the field. But, one can easily see that, even for a pure antiferromagnetic ordering like this simple ordering that, we found with Ibram Martin, a long time ago in this 3/4 filling in the triangular version of the SD model. So there, you find that, in the weak coupling limit, not in the strong coupling, the stable magnetic ordering corresponds to a triple Q ordering. So where each Q corresponds to the endpoints of the brilliant zone of the triangular brilliant zone, right? Triangular lattice brilliant zone, which in real space is a very simple structure, right? In real space is a 4 sublattice structure. So we have 4 sublattices A, B, C, and D. And in each of these 4 sublattices, the spins are pointing along the all-out directions of a regular tetrahedron, right? That is what I am indicating here. So although, the problem is 2-dimensional, we have a triangular lattice, of course, the spins, live in 3 dimensions, and they point along, these 4 directions. Now, from what I told you before, the flux, the effective flux associated with this phase corresponds to half of the solid angle spanned by these 3 spins on a given triangle. But given that these spins are pointing along these main directions of a regular tetrahedron, the solid angle is basically a quarter of the solid angle of the sphere, right? So that means that we have a quarter of a flux quantum on each of these triangular plaquettes for this antiferromagnetic ordering. if you put numbers here, right, if you remember that, well, a triangular plaquette in a solid will have an area of the order of a few angstroms squared, right? And you try to put, to apply a magnetic field such that, you can have a flux of a quarter of a flux quantum, right, in a few angstroms squared, you will immediately realize that you need a magnetic field of the order of 10 to the 4 to 10 to the 5 Tesla, which is really an incredibly high magnetic field. Just to get an idea, for those who are not that familiarized with the units, I mean, like, in the high magnetic field laboratory of Los Alamos, they can reach a bit more than 100 Tesla with pulse fields, right? So this is, 2 orders of magnitude bigger than that. So in other words, this antiferromagnetic ordering, it is clear that this antiferromagnetic, because the sum of the 4 spins is 0, can produce a huge orbital effect. And indeed, in this particular case, because it gaps out completely the Fermi surface, you get a spontaneous Chern insulator. So in other words, not only you get anomalous Hall effect induced by the antiferromagnetic ordering, you get a quantum Hall effect, right? So it's a very large effect. And this is interesting also because it means that, in principle, you could have spontaneous Chern insulator at ambient temperature, right? If you were able to stabilize this type of magnetic ordering at ambient temperature, then you could have a spontaneous Chern insulator at ambient temperature, which is, quite remarkable. Now, of course, so shortly after this work, we had, more than one discussion with Satoru Nakazushi, and, he said that he will look for these non-coplanar orderings in real materials. But, 7 years later, he came back with this material, manganese 3 tin, where, surprisingly, there is indeed a very large anomalous Hall effect. It's not quantum Hall effect, it's just anomalous Hall effect. But the magnetic ordering is coplanar. Right, so this material includes Kagome layers, right, that are vertically stacked. There are 2 types of layers that correspond to the red and the orange manganese ions in this plot. And in each layer, the system adopts this 120-degree ordering, which is not, it doesn't look like the usual one, right, simply because the vector chirality is opposite to the usual one. In other words, if I circulate around each triangle clockwise, the spins are rotating anti-clockwise, right? So that is the difference relative to the usual 120-degree ordering. But, this is a very simple and quite common, I would say, magnetic ordering, right, in triangular lattice antiferromagnets. And the important thing to notice is that, it is coplanar, right? So meaning that, we don't expect, at least for an SU2 invariant theory, to get any anomalous Hall effect out of this coplanar ordering. That said, well, the experiments of Satoru showed that there is indeed a very large anomalous Hall effect, at least for 2 planes, XZ and YZ. Here below, I mean, this magnetic ordering appears below 420 Kelvin. So they see that anomalous Hall effect in that temperature, below that temperature, and then below 50 Kelvin, the system becomes a ferromagnet. So, the story changes completely. Let me also say that, the anomalous Hall effect of this antiferromagnet is larger than the anomalous Hall effect that is reported, for standard ferromagnets like iron, cobalt, or nickel. So it is a large effect. And the question is, if, can we understand, what is the origin, or how does it work? How is that the interplay between spin-orbit coupling and this coplanar magnetic ordering can produce a large anomalous Hall effect? So for that, I will come back to this toy model, to this very simple SD model. And of course, now I have to include, it is clear that, we need to use the spin-orbit coupling in order to account, for this phenomenon. So I will incorporate the spin-orbit coupling, and the way the spin-orbit coupling appears, right, in this Hamiltonian is, in general, as we will discuss, I will discuss, also later, is, through the kinetic energy, right? If you have a hopping term now, unlike the previous case where the spin orientation was preserved by the hopping, now there is a U matrix, an SU2 matrix, right? Rotation matrix, that what it is telling us is that every time the electron hops, right, the spin principle rotates, right? And the rotation axis, right, is denoted by this A, boldface A variable, right? It's a bond variable because we have a U matrix for each bond. So we have this A kj. And the rotation angle is this variable alpha kj. Right? So this is a bond variable. It's an SU2 field, it's a bond variable. And as we will see in a moment, we can think of this actually as an SU2 gauge field where that is kind of frozen, right? I mean, these variables are not degrees of freedom, they are fixed. Once we fix the ionic configuration, if we don't let the ions move, these SU2 matrices are fixed. So, we can think that, we are coupling our matter field, our electron fields to an SU2 gauge field that is frozen, right? Now, how is this affecting our previous result, right? The very connection, for instance. Well, clearly before, right, for the SU2 invariant theory, I told you that the phase that the electron picks up when it moves from side J to side K is simply the argument of this overlap between AJ and NK. But now I have to account for the fact that the spin is rotating. So what I have to project is not NJ into NK, but UKJ applied to NJ that will give me this final spin orientation with NK. Right? So now we have, for the very connection, we have to compute the argument of this matrix element, right? Of the SU2 matrix UKJ between the initial orientation of the spinor and the final state of the spinor, right? So that is the way in which the spin orbit coupling will modify the very phase, right? Now, if you ask, of course, I told you before that, in absence of spin orbit coupling, the very phase has a geometric interpretation. It's simply the solid angle spanned by these three vectors, right? There is also a geometric answer in the presence of spin orbit coupling. Now you have to introduce 9 vectors that include the 3 that I considered before, N1, N2, and N3, right? Plus, for each bond, we have 2 additional vectors, right, that are obtained by applying, from these 2 equations, actually. But they involve, of course, N1 and N2 in the case of this bond, and the SO3 rotation matrix associated with the SU2 one that you have in that bond, right, applied to this vector. So basically, there is a geometric, the bottom line is that, all these vectors are defined by the 3 vectors N1, N2, and N3, and by the rotation matrices associated with the spin orbit coupling. So the problem with this geometric approach is, although one can immediately understand from the geometric approach that now, unlike this case, in this case, both collinear and coplanar orderings can produce a non-trivial very phase. It is more difficult, I would say, to get some physical insight of what is going on, what is the spin orbit coupling doing. So to get that kind of insight, I think it is more useful to use an algebraic approach. And in that case, what I'm going to do is I will go back to this problem of a single triangle, right? We let's say that we have these spin orbital fields on each of the bonds, right? So remember, I told you that we need vectors to denote the rotation axis of the SU2 matrix, and of course there is an angle alpha JL, for instance, associated with each of these vectors. Alpha will measure the strength of the spin orbit coupling. And as I told you before, now the very phase is the argument of the product of these 3 matrix elements, right? The 3 matrix elements of the SU2 matrices, right? Now, what I will do next is I will take advantage of the fact that this expression for the very phase is independent of the choice of the local reference frame, right, that we use for each of these 3 sites. In other words, if we make a local rotation of the spin reference frame, meaning that for each of the 3 sites, J, L, and K, right, we apply a local rotation, UJ, UK, UL, right? And then we transform the SU2 fields according to this expression. Remember, the SU2 fields are bond variables, so there are 2 U matrices, right? One from each of the 2 sides that the bond connects, right? That appear in the transformation of the SU2 fields. And finally, we also rotate the local moments according to the SO3 matrices associated with the SU2 ones that we are using for the local rotation. What you can see immediately is two things. One, that this transformation preserves the Hund's coupling, right? The Hund's coupling will remain isotropic, right? It will remain the same, actually, under this transformation. But not only that, this very phase will also remain invariant under this transformation, because for each U matrix that affects a bra or a ket, there will be a U dagger, right, that comes from the transformation of these fields U, right, in such a way that this very phase will remain independent of so it's the same regardless of what is the choice of the local spin reference frame. So what I will do next is I will use this freedom that I have for choosing the local reference frame to get rid of two of the SU2 spin orbital fields, let's say these two, and put everything on this bond, right? And the way we can do that is by choosing a particular local reference frame in which we don't do anything to the side J, for instance. We leave it as it is, that this is the identity. But for the sides K and L, we apply rotations that are related to our SU2 fields, right? So if you can verify that if you apply this particular transformation of the local reference frame, we can accumulate all the SU2 field in one bond. So we get rid of the SU2 field in these two bonds, right? And we put everything in one bond, but that comes at a cost that it is not a cost, but what is important to notice is that after this transformation, now the n vectors, right, the local moments, are pointing now in different directions, right? They used to point in these directions in the lab reference frame. Now in the local reference frame, we have nj prime, nk prime, and nl prime, right? So that is important to notice. Now, the other thing to notice is that this accumulated SU2 field that we have here on this bond turns out to be the product of these three SU2 matrices. That is the so-called Wilson loop operator. This is kind of a generalization of the notion of flux for U1 theories, but for SU2 theories. Here it is important where you start, right? Here we are starting from the side J. So we have UJL times ULK times UKJ. That product is also an SU2 matrix that has a rotation axis that I will call it AJKL, and a rotation angle, alpha JKL. Right? So now what I'm saying is this Wilson loop operator that is actually invariant also under this choice of the local reference frame, as long as this one is the identity, appears in only one bond. Okay, why this is useful? Because, well, now I can use the fact that I know the formula of the effective of the very connection already for these two bonds, because I got rid of the SU2 fields. And I only need to modify the formula for this last bond, right, where I still have a finite SU2 field. So when we compute the very phase, right, that the electron picks up when it moves around this triangle in the presence of a spin-orbit coupling, for this bond and for this bond, I still have the same formula as before. I have this solid angle, right, spanned by the quantization axis that I will choose now along the direction of the rotation axis of the Wilson loop. Right, so it's still this solid angle. So for this bond, the same story. Again, it will be this solid angle. But only in the last bond, in this one, we have an extra contribution, right? That comes from the rotation angle of the Wilson loop operator, right? So this alpha JKL appears here, alpha JKL over 2. And then in the formula of the solid angle, I mean, we see that the difference between the azimuthal angles phi, right, corresponding to these two vectors, is shifted by alpha also, right? So in a few words, right, what we are finding in the new reference frame is that the Berry phase is now half of the solid angle spanned by these three vectors n prime, right? So the underlying moments in the new reference frame, so that's the reason why here I have omega prime, plus a correction, right, that comes from the Wilson loop. In other words, this correction that is given by the Wilson loop will be 0 if the Wilson loop is the identity, if alpha is 0, right? So this is already enough to understand several things, right? So let's start with one of them. So let us consider the simple situation, right, of a coplanar magnetic ordering, similar to the case of manganese silicide, right? So our moments are in the plane, right? It's a 120-degree structure, now with the usual chirality. And we have also spin orbital vectors, right, that are pointing in these three directions. So in other words, the sum also of the three spin orbital vectors is 0. Okay, so I'm going to assume that the spin orbit coupling is weak, right? Which is actually a quite common situation for several materials. And what this means is that, you know, I will expand to first order in the spin orbit coupling in these rotation angles, right? So if we expand to first order, right, these SU2 matrices, right, the product of the three matrices will have basically a rotation axis that is simply given by the sum of the three individual vectors, right? Because we are linearizing. Essentially, what we are doing is we are, you know, expanding the exponential in Taylor up to first order, right? So essentially, you know, all these SU2 matrices commute up to first order, and then, you know, I just need to add the rotation axis, you know, JL plus KL, KJ plus LK to get the effective rotation axis of the Wilson loop. But clearly, in this case, this sum is 0, right? Meaning that to first order in the spin orbit coupling, the Wilson loop is identity. If the Wilson loop is identity, that means that we can gauge away, right, these SU2 fields, right? In other words, here we will have nothing. After choosing the new reference frame, we completely get rid of the SU2 fields in the three bonds, right? But here is the important thing to notice. The spins, right, the local moments now are pointing in a different direction, right? They used to be coplanar, but after this transformation, they are non-coplanar, right? And it's because of that, you know, in this new reference frame, they are non-coplanar, that we will get a non-trivial Berry phase, right? The Berry phase is pi minus 6 alpha, right? And what this simple example is telling us is something very important and very deep, which is that coplanarity is a non-covariant property. So coplanarity cannot determine whether you will have or not anomalous Hall effect, as, you know, one could infer from the SU2 invariant here, right? So we need a covariant expression for these emergent U1 gauge fields or for the Berry phase. And that is what I'm going to derive in a moment. Before doing that, you know, let me also discuss another important case of application, which is when, you know, again, the weak spin orbit coupling, but, you know, with ferromagnetism. So let's assume now that all the local moments are roughly pointing in the same direction, right? Or they are just pointing in the same direction. And again, because, you know, I'm assuming that the spin orbit coupling is weak, to first order in the spin orbit coupling, the rotation axis will be simply given by, you know, this sum, and then, you know, the normalization of this sum. So it's basically this axis. And what you can get, you know, again, if you use the formula that I just derived, is that the Berry phase that the electron picks up when it moves around the loop is given by the projection of the Wilson loop rotation operator, or the SU2, the strength of the SU2 field, along the direction of the magnetization. So you get this cosine of theta prime. And once again, you know, this has a very simple interpretation, right? I mean, if you have a ferromagnet where the moments, the spin moments are pointing along the z direction, right? And the spin orbit interaction is coupling the components that are 45 degrees away from the z direction, then, you know, you will have a cosine of 45 degrees, right? You know, acting on the, you know, that, you know, basically will renormalize the effective field that, you know, these electrons that are polarized along the z direction c. Right, so this is a quite simple result, but, you know, it is telling you that essentially you have to project, right, the SU2 field along the direction of the local moments. Right, so that again is something important to remember for what it is coming. Okay, so now the continuum limit. You know, so far I have done everything on the lattice, right? So I consider the simplest loop on the lattice, that is a triangle. So now let's consider an arbitrary loop, right, in the continuum. Right, so this, the base manifold is, let's say, the 3D space. This tau has nothing to do with time or anything. I mean, it's simply a parametrization of a loop in the 3D space. And what I want to do, once again, is I will assume that my electron is moving along this loop, right? And as it moves along this closed loop, it will pick up a phase, right? Again, like we did for the triangular, for the triangular loop. And of course, this phase, again, so this is the base manifold. Through the mapping into this N field, right? We have, a target manifold that corresponds to the surface of a sphere, S2. So when the electron moves along this closed loop, the N vector will also move in a closed loop on S2. And, what we can demonstrate, using essentially the same thing that you know from basic quantum mechanics, Berry phase in quantum mechanics, is that, once again, the Berry phase is simply given by the argument of the product of these inner products between N at two positions that are infinitesimally close, right? And when you replace this by an integral, right, you take the limit when delta tau goes to 0, you get the usual expression for the Berry phase, right? So you get, this is the Berry connection, you integrate over the closed loop, right? And you get, the Berry phase. Using Stokes theorem, you can again connect this Berry phase with the, with the solid angle spanned by this vector n along this loop, right? So this is simply the scalar chirality, right, integrated over the area enclosed by this loop, right? So now what we want to understand is how, again, in the continuum, this picture is modified, right, by the presence of spin-orbit cap. And so you don't get lost. What I'm doing here in the continuum is basically computing, again, the effective flux, right, the effective U1 flux, right, that is enclosed by this loop, right, by doing this, right? We know that, this solid angle divided by 2 corresponds to the flux in units of the flux quantum times 2 pi. So that is what I'm essentially doing. And with this, I'm computing essentially the distribution of flux or magnetic field, effective magnetic field, that is produced by a given distribution of magnetic moments, right? But so far, I did it, in the absence of spin-orbit coupling. When we add the spin-orbit coupling, the Hamiltonian changes because now we have this minimal coupling, right? So in the continuum Hamiltonian, right, the way we add the spin-orbit coupling is basically, we use, this minimal coupling to the spinor field, right? The spinor field represents the electrons, right? The spin 1/2 electrons. And then we have to shift, right, the derivatives by 4 vector potentials that now has 2 indices. This has an SU2 vector potential, right? Has a space index or space and time index, mu, can be 0, 1, 0, x, y, and z. And another index that, is the one that we contract with the Pauli matrices, right? So in other words, these A's are 2x2 matrices, right? They are acting on spinors. And what one can see is that, the space indices, mu, right, or the space components of A correspond to rotation, so to SU2 fields, whose rotation axis is perpendicular to the electric field at a given point, and to the direction of the bond. Remember, these are like bond fields, right? We are adding them to derivatives, so they are bonds. So the rotation axis, if you want, associated with this A field, as I said, is perpendicular to the electric field and to the direction of the bond. For the time component of the SU2 gauge field, what we get is a magnetic field. So here I added a Zeeman term, right, that appears once we do the minimal coupling, right, for the time component of the action. We get a Zeeman term, which means that the time component of the SU2 vector potential is proportional to the magnetic field. Right? So in this way, we see how electric field and magnetic field basically determine the 4 components of the SU2 vector potential. And once again, you can introduce a local rotation of the reference frame that in principle can depend not only on position, as I did on the lattice, but also on time. And we will see that, this expression of the action is covariant under this transformation, right? Again, we make a local rotation of the spinors, but that is we transform the SU2 gauge field in this way. This is essentially a gauge transformation, and will not change this action, right? It remains covariant. So, okay, so after noticing this, I go back to this formula for the very phase in the presence of spin-orbit coupling. I told you before that now we have to compute the argument of the product of these matrix elements, right, of the SU2 matrices, right? In the continuum, these SU2 matrices are exponentials like this one, but we can approximate them by by the linearized Taylor expansion, right? Because we are assuming that d tau is very small. So what really appears here is the tangential component of these SU2 gauge fields. And once you do this calculation carefully, what you find out is that the way in which the previous formula of the very phase is generalized is that now instead of having the usual derivative only, the mu here, that is what you usually have for the very phase, now we have to shift this derivative by this amount. So we get the so-called covariant derivative. That what it includes here, the new term is the projection once again of the SU2 gauge field. We are contracting this index A along the direction of the N field. Right. Once again, remember what I told you before. We project the SU2 gauge field along the direction of the local magnetization. Right, and that gives us the covariant Berry connection. Once again, if I use Stokes theorem, right, I have this basically integral over a loop. Now I use the Stokes theorem, it becomes an integral over the surface enclosed by that loop. We get the generalization of our formula for the very phase that has two terms. This term, right, is the covariant expression of the scalar chirality. So this is the covariant scalar chirality, while this is the projection of the strength of the SU2 gauge field. So this is the F mu newtons or of the SU2 field, but projected along the moment direction, right? So if you want, this is the contribution, that was identified originally by Karplus and Lattinger, right? This is the other one that I was mentioning that exists even in absence of spin-orbit coupling. But the important thing is that once you add spin-orbit coupling, you need a covariant generalization of this equation, right? Of this contribution, right? And this already shows that collinear or coplanar orderings can produce a non-trivial very phase, because again, once you have the covariant derivatives here, the three vectors do not need to be non-coplanar for this covariant scalar chirality to be non-zero, right? So this is really the general form and the most important result of this work, the general form of the very phase in the presence of spin-orbit coupling, this covariant expression. Okay, so in the last few minutes, I would like to show you how this math, can be applied to some extent to, to a real material, manganese 3 to again gain some insight. I'm going to use a toy model, so this is by no means a realistic description of the material, but I want to show you how by using a simple extension of the toy model, the SD model that I described before, one can understand several aspects of this anomalous Hall effect that has been reported by Satoru Nakatsushi in manganese 3. So what I will do is I still have this hopping and this Hund's coupling, right, for this material, and I will add another Heisenberg-like interaction between the local moments simply to make sure that I can stabilize this 120-degree ordering that has been reported for manganese 3. And then what I will do is for that 120-degree ordering, we will see what is the effect of that 120-degree ordering on the Berry curvature in momentum space. So of course, I have to incorporate the spin-orbit coupling, and for that, it is important to do a symmetry analysis. Basically, these spin-orbital vectors are similar to essentially the same. When you're working, with a strong coupling version of the Hubbard model, sometimes you have DM interactions, and you have to, see what are the components of the DM interactions that are allowed in each bond. Well, that is determined by symmetry considerations. So here is exactly the same story. The components of these vectors A, right, are determined by the symmetries of the material. So one can, as I told you here, we have, different layers, and these different layers are connected by triangles. So actually, something that you can learn immediately is that only these triangles that are connecting different layers can have a non-zero Berry curvature in real space, and it comes from this spin orbital vectors that, according to the symmetry considerations, can only have a component perpendicular here to the plane of the slide, and another component parallel to the AB plane, right? Again, here I'm showing, I'm showing the green layer on the top of an orange layer on the left, and then here is the opposite, the orange layer on the top of the green layer, right? So it's basically this or this kind of triangles. So these spin orbital fields, will again, introduce a non-zero Berry curvature, right, on these triangles that are connecting different layers. And that in turn, those kind of fluxes in real space, can produce a non-trivial Berry curvature in momentum space. So that can be computed by simply diagonalizing the Hamiltonian. It's a single particle Hamiltonian, so it's easy. And then computing this effective magnetic field that I mentioned at the beginning of the talk in momentum space, and then integrating that over the occupied states. Let me say that the sources of this effective field in the magnetic field in the momentum space are the sources and drains are Weil points, right? So we can identify the Weil points as basically, the sources of this non-trivial Berry curvature in momentum space. But as I said before, in real space, the real space Berry curvature that is producing this momentum space Berry curvature comes from these triangles that are connecting different layers. So here you have a plot of the distribution of the real space Berry curvature. And here you can see these red and blue dots correspond to Weil points, actually, that are generated in momentum space, and they are responsible for the non-zero Berry curvature that appears in momentum space. And when you use simple parameters here, I'm assuming that the hoppings, for instance, within each layer and between layers are the same, and I put the Hund's coupling that is twice t, and then I assume that the spin orbit interaction is weak. It's actually 10 to the minus of order 10 to the minus 2, right? Both for these bonds and for the interlayer bonds. We can get sigma yz, right? So a Hall conductivity that is of the same order of magnitude as the one that is reported in Satoru's experiment, right? So basically this tells us that okay, so this, as I said, we can, to do a serious calculation, one really needs first principles, advanced structure calculation, but this really helps to understand how is that the interplay between this coplanar magnetic ordering and the spin orbit coupling can produce an effect of the order of magnitude that has been observed. So to summarize, let me say a few things. First, that SU2 invariant systems, for SU2 invariant systems, the scalar spin chirality is what generates an effective magnetic field, right, that couples to the conduction electrons. But in the presence of spin orbit coupling, we need to generalize this notion. Actually, non-coplanarity is not a condition, right? It's not a requisite, to have anomalous Hall effect or to have an effective emergent U1 gauge field. The actual expression is given by this formula that, as I said, is the main result of the manuscript, and it tells us that both collinear and coplanar orderings can also produce anomalous Hall effect. And you may ask, why do we care? Well, we care because collinear and coplanar antiferromagnetic orderings are actually more common than non-coplanar orderings. And we also care because spin orbit coupling, it's always present and it's actually strong, in 5D or 4F or 5F electron magnets. So in principle, we can expect a large anomalous Hall effect, in this kind of materials, right? A large effective U1 gauge field produced by the combination of coplanar magnetic ordering with spin orbit coupling. And finally, because these SU2 gauge fields, as I said before, they are bond variables, meaning that they should be sensitive to pressure and strain. So that gives another knob, right, to control this emergent U1 gauge field through an external field. So thank you very much for your attention.
All right, thank you very much, Christian, for a very nice talk. Very pedagogical too. Appreciate that. I'm sure the audience does too. So now it's time for questions. I'm going to ask people in the audience to raise their hands if they have a question, so they can interact directly with the speaker, or you can just write a question on the chat window, and I will read it from there.
Okay.
So there is a question so Victor Yakovenko is asking, what's the reference to your work?
Oh, yes.
The main reference to your work. I think that's included in the abstract that I sent.
Right, and you can also
the mailing list, but it's not there.
It is here, and in the down here. Yeah, it's a paper that we published a few months ago in Physical Review B.
Also, Celso is asking, I think he's referring to slide 12 or 13.
This one?
He's asking whether these vectors AJK are the same as the ones before. So the vector.
You mean these ones here?
Right.
Or?
Right.
Yeah, these ones are always the same, and then right. I mean, like in the continuum, I call them capital A. But yes. So if that is a question, yes. Right. So these are always these are okay. These are the rotation. These are unit vectors, right? They only indicate the rotation axis. Capital A is the product of this alpha times A in the continuum.
Mm-hmm.
Right.
All right.
I don't know if that is the question.
Celso has another question.
Uh-huh.
Can I make a question here?
Mm-hmm. Sure.
Mm-hmm.
Okay. Could you go to the slide 24, please?
24?
Yes.
Yeah. Yes. Mm-hmm.
Okay. I think this. Oh, sorry. I think I should go to 25 or 26. I don't remember correct. Is that expression where you have the Algebraic curvature equation?
This one?
No, sorry. The magnetic field.
The magnetic field?
Yes.
Here, you mean?
Mm-hmm.
Yes.
No, sorry. Now I don't remember. I thought it was 24. Is that equation where you have the inverse of the difference between the energies?
Sorry. Yes. Here.
Yes, this one. Yeah, so
Yes.
Sure. Yeah, I look for this equation. I think you had a lot of numerical problem with that, right? Not.
Well, M is different from N, right?
Yeah, but I mean, essentially, if I understood correctly, your work here, what you are doing is try to look for this difference between heavy and light electrons, where when you have this spin orbit coupling is important, right?
Correct. So that will enter in this eigenstates, right?
Yeah, exactly. And usually, I mean, I don't know in this how was in this case, but usually you could have some potential energy surface that could be crossing each other, or could have some body cross in this case, right?
Yes.
Yeah, and my question to you is the following: what happens when you have, for example, a conic section or something like that in this equation?
When you have, sorry, what?
A conic intersection. I mean,
you mean like a while point, or?
Yeah, something like this.
Yeah, so you can still compute the integral, right? This integral here, and get a value for sigma mu, right? So I mean that's so right. I mean so wherever you have a source of a drain of very curvature, you have a singularity. I guess that is what you're pointing.
Yeah, exactly. Mm-hmm.
Right, but you can still integrate around this singularity and get a finite value of this sigma mu, right? So numerically you can do it. That's what I'm trying to say.
Yeah. This is this is my question.
Oh,
Yeah.
I see. Maybe, if you want, I can contact you offline and show you more details of the numerical.
Yeah. I actually I'm hunting here more. I
Okay.
would say numerical detail about this,
Yeah,
because
right.
I already struggled with this problem before, and I had
Okay.
a lot of problem to get around.
Okay.
And another question, it's a more, I would say, force you go to a more realistic, I would say, material like perovskite, for example.
Yes.
Where these spin-orbit couplers are really important. I mean, for my understand about this material, and I'm doing some work, some projects on that recently, is that there is some, I'd say, this spin-orbit couple is causes some huge effect between these heavy and the light electrons there. And my question to you is, could your model try to fit some physics from this more realistic problem, or this is more for this, I'd say, symmetric material like you had before? Like
you mean like manganese?
Yeah.
Right. So yeah, that is a very good question. I mean, like in principle, okay, you can imagine also, working with Kondo lattice model, right? For if you are thinking of electron materials, I could also introduce again. I mean, Kondo lattice model in the end is the same as the model, right? Treat the local moments classically, and then there you can expect a bigger spin-orbit coupling, meaning for the conduction band, you may have larger values of these alphas, right? I mean, this parameter alpha is what controls the strength of the spin-orbit coupling. But the problem is that you will never do something very quantitative in that way, right? Because something that I didn't say is that and probably it is indicated in this figure. Let me show you. Here, this is the sigma yz, for instance, in this model as a function of the chemical potential. So you can see that it is changing very fast, right, as a function of the chemical potential, right? So it is very sensitive to details like the chemical potential, and then to other microscopic details. So I think one cannot avoid doing a realistic calculation if you want to have something that is quantitatively accurate. I will say, these kind of simple models or toy models help to develop some understanding of, where is the very curvature in real space, coming from. So where is the effective flux in real space, the U1 gauge field in real space, right? That is producing, the anomalous Hall effect. So for instance, for manganese 13, you will say, well, it's these triangles, right? So, if you want to increase the spin-orbit coupling, it should be one should try to do something that modifies, the hoppings on these triangles that are connecting these layers. I guess for an F electron material or something like that, one should try to do a similar kind of analysis. In principle, I don't see how, why one cannot do it. Right? Again, to develop, more insight, not to have a quantitative theory.
Yeah, I understand. The main idea is try to get the trends of the physics of the material. Yeah.
Right, to get trends, or right to say, well, probably this is the bond that we should be modifying, or the ion that we should be replacing if we want to have a stronger, effect.
All right, we have a question from Andreas Kreisel. Please, yes. Andreas, go ahead.
So in the beginning, you were introducing this geometrical interpretation. I mean, the three vectors, the n1, n2, and 3, yes. And then the more complicated version of it with a spin-orbit coupling. Yeah. So you didn't spend much time in this, but my question would be, can you shortly explain how these auxiliary vectors behave in the limit spin-orbit coupling going to 0?
Yeah, that is a good question. I mean, let me go back to that equation. Here,
these ones, yes.
Yeah, you are asking about these vectors, right?
Yes, yes. What is the interpretation in spin-orbit coupling going to 0 to get a feeling?
Yeah, so
what I mean,
one has to be careful with that limit because, right, strictly speaking, right. I mean, when the spin-orbit goes to coupling goes to 0, one should get back this area, right?
yes.
Here, and yeah. So I think probably in that case, so right, what should happen actually is that these two vectors should be on the geodesic that connect these 2 points, right? So then the area of this nonagon becomes the same as the area of this triangle. But you're right that one has to be careful with these vectors because, for instance, if you consider a collinear, like if you consider a situation where these 3 vectors are parallel to each other, and 1 and 2 and 3 are ferromagnetically aligned. As I explained, if you have a spin orbit vector that is also parallel to them, you can have a non-zero Berry curvature, right? It's basically the Karplus and Lattinger story. And if you put blindly, right, that case in these 2 formulas that I have down here, it will look like everything is ill-defined, right? But if you take the limit, the interesting thing is if you take that limit, right, coming from a non-collinear situation, towards the collinear one, you can see that the area is well defined. So you will get the correct Berry phase. It's just that the nonagon or the polygon, sorry, on the sphere is not always the same. So you can approach the same area from different polygons. Right. So, but again, it's not the question that you were asking. It's more like, if you consider the simple case where these 3 vectors are parallel to each other, so they become a point, right? And also the spin-orbit coupling is parallel, right? So of course you have magnet. It's the case of the ferromagnet, right? You have, ferromagnet, right? And the spin-orbit coupling is along the same direction, right? So we know that should produce a non-zero Berry phase, right? Because we have this Karplus and Lattinger story. But according to this formula, you will find out that you expect that all these vectors should be parallel to each other, and that is not true. I mean, so actually these 2 formulas are ill-defined in that case, right? Because you will get that n cross S is 0. So one has to take the limit in this. So that is a delicate, limit, and you get the correct result.
Okay.
Yeah, but as I said, it is true that if you look carefully into this, I mean, the story is also that the reason why you have to introduce these vectors is because you really need to decompose that unitary transformation. I mean, this SU2 field into transformations that go along the geodesic always, right? So that is the reason why you need to introduce these vectors. I mean, like it is explained in the paper, and it will take a bit more, but. I'm glad to give you more details in offline if you want. How these 2 vectors appear. Adrian, I think we cannot hear you. Okay.
I'm sorry, Nancy. Sandler has a question. Please, Nancy, go ahead.
Yeah. Hi, Christian. It was a very, very nice talk. I enjoyed a lot. And I have kind of a naive question. If I understand the idea, you are incorporating the spin orbit through a unitary transformation that rotates the spinors in the kinetic energy. Now, what about changes in the kinetic energy that are independent? The spin orbit could change the dispersion too, independent of the spinor orientation. How would you incorporate that within this model?
You mean changes of the kinetic energy term that they like, for instance, changing the magnitude of the hopping, but not the.
For instance, yes, exactly.
Yeah, no, that's an excellent question. So, right, I mean, the way, well, I can still compute the whole conductivity or the Berry curvature in momentum space for different hopping or different magnitudes of the hopping, right? So you're right. So that is the way I will incorporate that. But your question points to a very important thing. That is, knowing the Berry curvature in real space does not determine the Berry curvature in momentum space, precisely because of what you are saying. Because if I change the magnitude of the hopping, not this SU2 metric, but let me see if I can go to the where I want to go to. Yeah. So what
Yes,
you are,
there,
if I understand
exactly.
it correctly, you want to change the magnitude of this Hawking, right?
Yes.
Exactly. So precisely. So right, the Berry curvature in momentum space will change the distribution of Berry curvature in momentum space, but the distribution of Berry curvature in real space is not changing.
It's not, yeah, because that would depends on the orientation of the spinor.
So, and that, right, that is an excellent point that, shows indeed, because, a common question is, can you tell what is, the Berry curvature in momentum space, knowing the Berry curvature in real space? The answer is no, precisely because of what you are saying. Right? So, I have to do the calculation. So, right.
Okay. Okay.
But,
Thank you.
Yeah, you're welcome.
All right. Any other questions from the audience? All right. If not, I'm going to thank Christian one more time for joining us, and I'd like to thank the audience as well. And this video is going to be posted on YouTube, so you can enjoy it at will. All right. Looking forward to seeing you next week in our next seminar, and have a nice week. Goodbye.
Thank you very much.